In this session, we are going to see how to write a basic assembly language program and simulate the program using Keil Microvision 4 IDE. So this is Keil Microvision 4. You can click on that and open the IDE. So this IDE is used for writing assembly language program as well as C programs in ARM microprocessor or microcontrollers. So first of all, you need to create a project. So for that, you can click on this project tab, then click on new Microvision project. Then what you want to do is you need to create a project folder, right? Why you are going to create a project folder? Because while you are creating a project, there will be more files associated with that project. So all the files should be kept in a project folder, otherwise it will be scattered here and there and compilation may not happen properly. So for that, before creating a project, you need to create a project folder. And while creating the project folder, one more thing you need to keep in mind, that project folder should not be created in My Documents or in desktop. Why? Because if you are creating a folder in My Documents or desktop or in downloads, the path length will be very long. Say for example, My Documents or desktop, what will be the path? C Documents and Settings, then username / desktop. So that means the path for representing, the complete path for representing that folder name will be very long. So in Keil IDE and most of the IDEs, the path length for a project folder should not exceed 64 characters generally, right? So in order to have lesser number of characters in the path for the project, what you will be doing is the project folder should be created under any one of the drive directly. So here I am having C drive, D drive, E drive, etc. For example, I am going to create the project folder directly under D drive. I am not going to create it in desktop or in downloads. So I am going to create it directly under a folder, under a drive. So click on D drive, then click on new folder, right? So under D drive you will be creating a folder, so click on new folder, then I am giving a name for the folder. So this will be my project folder, so I am giving ARM project folder. So I have created ARM underscore PRJT folder, that is ARM project folder. Now you can open this folder. So whenever you are creating a folder which is having more words in the folder name, we can use underscore instead of space, because in some of the IDEs the space will not be accepted in the folder name. So as a general principle, wherever you are creating a folder name with more than one word in the folder name, you can use underscore for separating the words. Now I have opened the project folder. Here I am going to give the project name. So I am giving, say, ARM underscore basic. I am going to give ARM underscore basic as my project name. So while creating a project name, you need to give the project name alone. Don't give any extension, because by default .uvprog Microvision project will be added to the project folder, project name. So you need to give only the project name, no need of giving any extension. So I have given the project name, then give save. So this project will be stored inside this project folder under D drive. So I am doing save. So I have created the project. Next step is you need to select device for target, right? I have created a project. For that you need to select a target device. So for this example I am going to use LPC2148 microcontroller as my target. So what should I do? LPC2148 is developed by a controller known as NXP. So you can see NXP here. Towards left of that you can see a plus symbol. Expand that. For expanding you can click on that. So all the controllers under NXP will be shown. Here you scroll down and select LPC2148. LPC2148. So while you are selecting the microcontroller, all the processor details and peripherals will be shown here corresponding to 2148. So you can see it is having ARM7 TDMIS as the processor, 512 KB on chip flash, right, and all the peripherals will be shown here, right. Then you have selected LPC2148, click on OK. So now it will ask for another dialog box. Another dialog box will be coming. Here it is asking for whether do we need to add Philips LPC2100 startup code to this project folder. It is asking whether do we need to add startup code into this project folder. So startup code contains all the startup files required for a microcontroller program to work. So in this case, the startup code contains all the SFR descriptions and so many things. All the special function registers will be mapped into its corresponding name in the startup code. But since now we are going to do basic assembly language program, you are not going to use any SFRs. That means you are not going to use any other peripherals. Only basic programs you are going to do in assembly. So in assembly, since you are writing the program, you don't need a startup code. Whenever you are going to program peripherals in embedded C, then only startup code is required. Now since you are going to write basic programs in assembly, startup code is not required. So we can give no. We don't need to add startup code. So you can give no. Don't give yes, you need to give no. So now you can see this is a project explorer. Under project explorer, target 1 will be created. When you are expanding this plus symbol, you can see one source group folder is there. So whichever assembly program you are going to build or compile, that should be added to the source group, right. So now I have created a project. Next step is you need to create the program. So for that I am clicking on file new or this new icon. I am going to click on that. So a new text editor will be coming here, right. So here I am going to type the program. What is my program? So before typing the program, you can enable caps lock. So for time being, I am going to type the whole program in capitals, right, because certain keywords are to be given in capitals, and your instructions can be in capitals or in small. So in order to avoid all those confusion, complete program I am going to type in capitals. So first thing you need to type is a assembler directive area. Then I am using tab or space you can use. For time being I am using tab for separation. Then name of the program, so addition, comma, which area you are using, code, comma, attribute, I am giving it as read only, right. So area, addition, that is the name of program, code, it is area, read only is attribute. Next one, you are giving another assembler directive known as entry shows that from next line onwards your actual program is starting. Then you are giving move, again I am giving tab, it is not space, it is tab, move r1 comma #1. So you are moving 1 to a register known as R1. Similarly, you are moving R2 comma #2. So second number, that is 2, I am moving to R2. Then I am going to add these two. So add tab, and the result should be stored in R0. So add R0 comma R1 comma R2. So we will be adding R1 and R2. Result will be stored onto R0. Then before giving the short jump, you can give end, and we will see what will be going to happening. So as the last line you are giving end, right. So this is my basic program. One more statement you need to give here, short jump, that we will give later. Before that we will see what will be happening if you are not giving that short jump, right. So that we are going to see. So now I have typed the program. Next, what should I do? I need to save it as .s file. So click on file, click on save as. Then always verify that you are going to store the program under the project folder. Which is my project folder? ARM_PRJT. Right. So inside I am going to give a name for this program. that is add. But here whenever you are giving an assembly or going to save an assembly language program, you need to give file name .s. .s will be the extension for assembly in ARM. So you can give arm.s, right? So you are going to save this program as arm.s into this folder. Save. So now what is the next step? So I have saved the program, I have created the project. Next step is you need to compile this program or assemble this. Since it is assembly language program, you need to assemble this program, right? So for that you will be doing something known as build. So for building, that means instead of assembling the program directly, you are building the project as it is. So I have created a project known as arm_basic. I am going to build this project as it is. So for that you can click on this icon. You can see here build. Can you see F7 or build? So when you are giving build, you will be getting an error. Target has no object files. Target not created. Right? So when you are giving build, you are getting this target not created. Target has no object files. You are getting this error. Why? Because you have created a program separately. You have created a project separately. When you are giving build, I told you are building the project, not the program. You are building the project, but the project should contain the assembly language program which you want to build, right? But now what is happening? You have created a project, but project is not containing the program what I have created now, right? Now program and project both are separate. You need to add this program into the project. How will you do that? For that you need to right click on source group 1. Right click on source group 1, then select add files to group source group 1. Right click on source group 1 in Project Explorer, then add files to source group 1. Then again verify that whether you are going to the same project folder. Now you are going to the same project folder, you are inside the project folder, but we are not able to see that program which you have saved before. Why it is like that? We have already saved the program as add.s here itself, but I cannot see it. Why? Because you have selected by default files of type which should be shown here will be .c file. Files of type is .c file. But in my case, my files is of extension .s. So select this, select the next one, assembler source file .s, .src, .a, etc. So select this file type arm source file .s. It is very important, then only you can see that. Now your program file is visible. So select that program file, click on add. Right? Select the program file, click on add. Then you can close this window. Don't keep this window here. It will not be automatically closed. You need to close it. So select this program, click on add, then close it. Now in the Project Explorer under source group 1, you can see 1 plus. When you are expanding this, you can see your program. When you are double clicking, you can see this is your program. Now I have added the program into the project. Now the process is complete. Then you can give build F7 or build. Now you can see that another error is coming. What is that? Unknown opcode, addition code read only, expecting opcode. A label was found which was in no area. Two errors are coming. Unknown opcode, that is the main error. Then a label was found which is in no area. Why that is coming? Why it is coming? Why? Because in the case of ARM assembly language program, the first column of the program is dedicated for specifying a label. Right. First column is dedicated only for specifying the label. While we have seen the program explanation in the previous class, so if you want to have more details regarding the program explanation, you can go and refer my previous lecture. There I have explained this program completely. So in that class we have seen that you are using a label known as stop branch stop we are using. So in the first column only that label should be specified, nothing else can be specified. That is why it is showing unknown opcode area. Now because area is taken as a label and this is taken as opcode. So in the first column only label should be there, nothing else. So how will you do that? So you can give first column as vacant here. So how will you do? Click before area, give one tab. Similarly, give one tab for all the statements. You are only allowed to give the labels in the first column, nothing else. If you are writing any assembler directive or if you are writing an instruction, it will give an error. You should give only labels in the first column. So I am giving one tab for all the instruction. Then I am giving build. Whenever I am giving build, automatically it will be saved. So you can give build. So now you can see that program has been assembled, it has been linked, and finally you are getting the executable. So you are getting 0 error 01, 0 error 0. Now I have compiled the program. Then what should I do? I have built the program. Next step is you need to simulate the program and see whether you are getting the output. So how will you do that? For that you can click on this D symbol, the start stop debug session. Start stop debug session. It is for simulating or debugging the program. So you can click on this. So you'll be getting a window like this, evaluation mode, running code size 32K. You cannot give programs more than 32K in the evaluation version. You can give OK, no problem. So now you will be, this is a debug session, right? So in the debug session, what all things you can see? On the left hand side, you can see all the registers which are present in the current mode of operation, right? These are the registers. These are the values present or data present in the registers. Then you can see the CPSR and SPSR. So R0 to R15, then CPSR and SPSR of current processor mode you can see in this left hand side as in the registers window, right? And which is your processor operating mode now? Supervisor mode. So I have already told, whenever you are resetting the processor or when you are starting the program, you will be always in the supervisor mode. And in the supervisor mode, what all registers are visible? R13, that is stack pointer, R14, that is link register, and SPSR. So while the processor is in supervisor mode, only these three registers will be visible. In addition to that, R0 to R12 will be visible. So R0 to R12 of the user mode of operation will be visible in supervisor mode also. So R0 to R12 will be visible. Then R13, R14 and SPSR of supervisor mode will be visible, right? So R13, R14 and SPSR of supervisor mode and R0 to R12 of user mode. These are the registers visible in supervisor mode of operation. So by default, when you are starting an assembly language program, you will be in supervisor mode. That is why it is in bold. So now the current operating mode is supervisor mode. So this is the registers. Then here you can see in this window, you can see the disassembly listing. So in this window, you can see the disassembly listing. Disassembly listing means whatever program you have written, the disassembled form of that program. That means you are writing an assembly program. When you are doing disassembly, what will happen? That assembly language program will be converted it into corresponding 32-bit opcode, right? So you can see here move R1 comma hash 1. This is your program, assembly language program. When you are disassembling this move R1 comma hash 1, what will be the 32-bit opcode? This will be the 32-bit opcode E3A01001, right? So E3A01001 is the 32-bit opcode for this instruction. And where will be this 32-bit opcode stored? In an address location 0000, right? So in address location 000, this will be stored, right? So and how it is stored in this address location? In the form of bytes. We have already told in the last class. So in 000 location 01 will be stored. In 0001 10 will be stored. That is a second byte will be stored. In 0002, what will be stored? A0 will be stored. Then in 0003, E3 will be stored. So from 000 to 003, that is 00, 01, 02, 03. These four locations are used for storing the 32-bit opcode for move R1, #1. Right. Since you are having 32-bit opcode, four locations are used for storing this value. Similarly, this is the opcode for the next instruction, E3A02002. This is a 32-bit decoded opcode for move R2, #2. So this 32-bit opcode will be stored from which location onwards? 4 onwards. Why? Because 0, 0, 0, 1, 0, 2, 0, 3. These four locations will be used for storing this 32-bit number byte by byte. This is LSB, this is the next byte, this is the third byte, this is the fourth byte. So 4 locations are required. Then from 04 onwards, this will be stored. 04, 05, 06, 07. These 4 locations will be stored used for storing E3A02002. Right. So in 04, 02 will be stored since it is LSB. 05, 20 will be stored. 06, A0 will be stored. 07, E3 will be stored. Right. Then in 08, what will be stored? Add will be stored because that was the last instruction. So add R0, comma this one. What is the decoded opcode? E081002. This will be stored in 08. Right. Then we have seen already in the last class. Then the remaining codes, remaining location, what will be there? Complete zeros will be there. That means there is no program code. From 00C onwards, we have not written any program code. So what I told, when you are executing 00C, the processor will move on to which mode of operation? Abort mode of operation. Which abort? Prefetch abort mode of operation. Why prefetch abort? Because there is no instruction in 00C. So we will verify that. So now we are going to execute the program line by line, and here you can see this is the actual program, right? So here you can see a yellow arrow. What does this yellow arrow shows? This is a program counter. So program counter points to the next address of the instruction that is to be executed. So what is that instruction that is to be executed? Program counter is pointing to 0004. So in the next cycle, this instruction will be executed. What is that instruction? Move R1, 1. What does it mean? 1 will be moved to R1. Now what is the content of R1? You can see here R1 is having 0. So you need to execute this one line alone. How will you do that? You can click on this step icon or F11. When you are clicking that, program counter has incremented to the next line. That means in the next click, this line will be executed, right? And this green color shows that this first instruction has already been executed. What is that? 1 will be moved to R1. So now you can see 1 is present in R1. 1 is moved to R1. When you are executing the next line, what will happen? 2 will be moved to R2. Now R2 is 0. So for executing that, again you are clicking on step. So now 2 has been moved to R2. 2 is present in R2. Again, the program counter has been incremented to the add statement. So now if I am pressing the step button again, add R0, R1, R2 will be executed. So after executing, what we are expecting? R1 is having 1, R2 is having 2. These two will be added. Result will be taken to R0. Right, that means R0 will be having 3. But here that won't happen. Why? Because when you are clicking on this, the program counter will go to the next location, but there is no actual program. So you can see that. So now when I am clicking on this, what happened? Prefetch abort has taken place. ARM instruction at this location. Right. That means it is somewhere else. Because when you are clicking on the next button, it will program counter will go to the next line, next instruction, but program instruction or instructions are not there from the next line onwards. So the processor don't know what to do. That means it is trying to get the instruction but it is not getting that instruction. So whenever the ARM processor is not getting that instruction, what will happen? It will move on to a mode known as abort mode. That is why it is in bold. And which kind of abort? It will go to an abort known as prefetch abort. Right. So since program instructions are not there after add, the processor will go on to the next line and it cannot find any instruction there. It will move on to the mode known as abort mode of operation. Right. So when you are doing programs, you should avoid this. We should allow the program counter to increment to a location where instructions are there. If instructions are not there, it will go to abort mode. We should avoid this. So how will you avoid that? By incorporating the short jump. You should not allow the program counter to go to a location where instruction is not there. That means you are telling the program counter to keep on executing a particular line infinitely. That line is known as short jump, right? So we need to modify that. So whenever you want to modify the program, you need to go out of this debug session. So how will you go out of this debug session? Once more click on this D. So you will go out of the debug session. Now you came back to the editor. Here you can edit the program. What is the short jump you are adding? Stop. Then you can give space or tab. Now I have given space. B, tab, stop. So stop, B, stop. That means you are adding a short jump. You are instructing the program counter or processor to execute this line infinitely. So and whenever you are making a change in the program, don't forget to give build. Whatever change you are making, you should give build again. Then for debugging, you can click on start stop debug session. Right. Now we can see the execution of program. So when you are clicking on once on the step button, 1 will be moved on to R1. Now 2 will be moved on to R2. Next, when you are pressing this, what will happen? Addition will take place. 3 will be moved on to R0. So you can see that, right? So now you can see that 1 and 2 present in R1 and R2 will be added and the result is taken back to R0. Previously this result we are not getting this result. We are getting prefetch abort. It was written here prefetch abort and processor will move on to prefetch abort mode. But now you can see that it is remaining in supervisor mode itself. It is not going to abort mode. Why? Because in the next line 00C you are having an instruction. What is that? Branch to this instruction itself, this address itself, that is B, this address. So when the processor is executing this, what will happen? When it is executing it, processor will go on to this location itself. How the processor is moving to this location? Program counter will be incremented with this itself. So now how many times you are pressing on that step button, program counter will not be incremented to the next line. It will be as same as that itself. Why? Because you told the processor to branch to this instruction itself. So this instruction will be executed infinitely. So by doing this, you are protecting the processor from going to abort mode. That is one advantage. And one more thing you are doing, you are not allowing the code to execute more than once. Because when you are adding 1 and 2, you should get 3. You should not keep on adding something else to the result. So you are in turn protecting the program by executing it by once. The program will be executed only once and the processor will not be allowed to go to abort mode of operation. Right? Now it remains in the supervisory mode itself and you have executed the program and got the result in 3 in R0, that is 3. Right? So this is how you are writing an assembly language program for addition of two numbers in Keil Microvision IDE and simulating or debugging the result using Keil IDE. Thank you.